There is a moment that people of a certain age remember with an almost embarrassing precision. You are kneeling in a field, or standing at the edge of a driveway, or crouched over a workbench where the concrete is stained with decades of fuel. The model aircraft is in front of you, held by someone else if you're lucky, or braced against your knee if you're not. You have primed the engine. A tiny two-stroke barely larger than your fist, made from machined aluminum and case-hardened steel by people in upstate New York who understood what this machine was supposed to do and built it to do that thing without apology. And you are about to attempt to start it. The fuel is methanol and castor oil and whatever percentage of nitromethane you could afford. And it smells like nothing else that exists in the ordinary world. Not gasoline, not diesel, not any of the domestic fuels the ordinary world runs on. Model fuel is its own category of sensory experience, organic and sharp at the same time. The castor oil giving it a faint sweetness underneath the chemical bite. The nitromethane adding a heat you can feel in your sinuses if you lean in too close. You have been warned about leaning in too close. You have leaned in too close anyway, because you are 12 years old and the engine is not running and you need to understand why. You flip the propeller, nothing. You flip it again, nothing. You prime the engine with a drop of fuel on the intake and flip it again. And this time it coughs. A single, violent, one-syllable statement that is somewhere between a mechanical bark and a small explosion, and then goes silent. The propeller is still. The needle valve wants adjusting. You reach for the needle with fingers that are already oil dark, that will carry the stain for 2 days regardless of what soap does, and you turn it a fraction richer and try again. The third or fourth or sixth attempt, the engine catches. Not yet, but with a sputtering urgency that has intent in it. That is trying to become something, and with the right needle adjustment, it crosses from trying into running. And then it is running, and the sound it makes is everything. It is a sound a human body responds to before the mind can interpret it. Not the muffled rumble of a car engine, not the polite hum of a generator, but the raw, reedy, urgent scream of a two-stroke working at the top of its ability, which is the only way a two-stroke knows how to work. That sound, that specific, unambiguous, utterly essential sound. You're holding something that in 1949 represented a genuine achievement of American mechanical thinking. The OK Cub cubic inches of displacement, first in the United States at that size, produced by the Herkimer Tool Model Works of Herkimer, New York, was not just a product, it was a gateway. The question worth asking before we know the answer is, a gateway to what? And the second question, which takes the whole story to fully address, was OK Cub outpaced by the technology that followed it? Or did the world that valued engines like it quietly disappear? The answer is one of those answers that takes a long time to arrive at, and that arrives quietly, without announcement. Charles Brubeck was a machinist in Herkimer, New York, a small city along the Mohawk River in the center of the state, a place whose industrial history is the kind that does not make it into textbooks, but that shaped American manufacturing through the patient accumulation of skilled labor over generations. In the summer of 1937, his 20-year-old son brought in a model airplane engine belonging to a friend, needing repair. Charles looked at it. Charles, being a machinist with access to a machine shop and the specific disposition of people who look at existing things and think they can do better, decided he could do better. Within a year, he had formed the Herkimer Tool and Model Company with his son Charles Jr. and a partner named Harry Bliss. Bliss retired after a year, and the Braybecks bought his share for $700. What followed was not a rags to riches story. Because Herkimer was not rags, it was working class, skilled trade, small city New York, which is its own particular thing, distinct from poverty and distinct from comfort. What followed was the story of a machinist who had identified a need, built a product to meet it, and found that the product was good enough that the need turned out to be larger than he had initially supposed. The initial OK engine was a cubic inch displacement ignition model, substantial, designed for larger free-flight aircraft and early radio-controlled applications that the pre-war modeling world was beginning to explore. By 1939, Herkimer had a 10 and a 1 cubic inch twin-cylinder engine built for military target drone applications. Charles held patents for engine design improvements that minimized heat distortion during manufacture, and for a method of fabricating a crankshaft using a cooling jig to prevent welding heat from softening the assembly. These were not decorative patents. They were the documentation of genuine engineering problems, genuinely solved by a machinist who had worked through the problems by working on actual machines. Between 1939 and 1949, thousands of OK engines were produced. The war years were navigated partly by supplying the military. The one twin had drone applications, and partly by continuing the civilian production that was permitted. By the end of 1953, the company would report having sold more than 1 million engines and having 700 distributors distributed across a country where model aviation was becoming, for the first time, a genuinely mass activity rather than the specialized pursuit of a devoted few. The event that changed this trajectory was the 1949 introduction of the OK Cub, the glow plug engine, as opposed to the ignition engine, which required a separate battery and coil system to fire, had been developing for several years, and the cubic inch displacement was the frontier of miniaturization at that moment. Small enough to power control line models that a beginner could manage, affordable enough to put in reach of the mass market the hobby was developing. The OK Cub was the first glow plug engine produced in the United States. It arrived in June 1949 to what the hobby press described as a very enthusiastic reception, which is the language of restraint for what was, in effect, the introduction of an entirely new category of accessible power. By the end of 1949, the Cub series had expanded to include N cubic inch models. The design was honest. A radially ported glow motor in a bright pressure die-cast aluminum alloy case, a blued steel cylinder with integral cooling fins, a screw-in head machined from hexagonal aluminum bar stock. The crankshaft carried a square-cut induction port. The piston was hardened steel. The connecting rod was a die-cast light alloy. The materials and methods of a competent American machine shop applied to a specific problem with the intention of producing a reliable, affordable, reproducible result. What they produced was an engine that would appear in kit plans from scientific models, whose publications rarely showed a nose without an OK Cub diagrammed in it. An engine that the designers Walter Musciano, Paul Plekin, and Paul Delgado specified in their plans almost as a matter of course. An engine that Comet, when it moved into ready-to-fly plastic control line aircraft, specified in its models because the Cub was reliable enough to go into a product sold to people who had never started a model engine before and would receive no instruction beyond what came in the box. Understand what OK Cub meant in American model aviation culture you have to understand the specific world it entered. Post-war America. The America of 1949 and 1950 and 1952 was experiencing a particular kind of energy around making things, a cultural disposition toward building and tinkering and understanding the physical world through direct engagement with it that seems, from the present, almost exotic in its specificity. The men who came back from the war had in many cases spent years in intimate proximity to machines. Aircraft engines, vehicle engines, the 1,000 mechanical systems that a modern military depends on, and they returned with a comfort with machinery that translated directly into the workshops and garages and basement spaces of post-war American life. They built model aircraft as recreation, as a continuation of the relationship with flight that many of them had formed during service, and as something to share with the children growing up in the suburban houses that the post-war economic expansion was producing at a pace with no historical precedent. The hobby shop was the institution through which this culture organized itself commercially and socially. Not a big box retailer, not an online marketplace, but a specific kind of small business, usually a modest storefront, sometimes attached to a sporting goods operation or a hardware store, staffed by a person who had been in the hobby for years and who understood the difference between the engines and the kits and the covering materials and the fuel with a specificity that made the transaction educational rather than merely commercial. You went to the hobby shop not only to buy things, but to be told what to buy, and why, and how, and what to do when it did not work the way the instructions suggested it would. In this environment, the OK Cub occupied a specific and important place. It was not the most powerful engine. The competition engines, the Fox and the Vico and the McCoy speed units, were faster, more powerful, tuned for performance at the cost of reliability and ease of operation. The OK Cub was tuned for something different. It was tuned for the person who was new to the mechanical relationship between an engine and a model, who needed an engine that would reward patience with operation, that would start if you followed the procedure and run if you had it adjusted correctly, and that would not destroy itself if you leaned it too far for 30 seconds. This is what accessibility means in a mechanical context, not simplicity. The OK Cub was not a simple engine. It was a precision miniature two-stroke that required understanding to operate, but accessibility. The difference between a machine that allows a beginner to succeed if they pay attention and a machine that rewards only the already expert is, in fact, the difference between a hobby that grows and a hobby that remains the province of specialists. A large number of companies recommended OK Cubs for powering their models. Scientific kit plans rarely showed a nose without a cub diagrammed in it. Walter Masciano's designs, Paul Plecken's designs, the cub was specified so consistently that it became almost invisible as a choice, the default answer to the question of what engine to use when you were starting out. If this sound, that bark, that small mechanical urgency brings back something you thought you had left behind years ago, take a moment to like this video and subscribe. Not for the algorithm, but so stories like this do not fade into silence. The people who live this world are still here, but not forever. The record of what it meant to kneel in a field with a small engine in your hands and coax it into life deserves to be kept. The starting ritual deserves its own account because it was not incidental to the experience. It was the experience, or the first portion of it. Learning to start an OK Cub was itself a small education that people who went through it remember with a combination of affection and relief that they no longer have to. The primer, A single drop of fuel on the intake, no more, or the engine floods and you wait for it to clear before you can try again. The glow plug connected to the battery, which heats the coil to ignition temperature. The propeller, which you flip by hand, using one finger along the blade to keep your grip away from the arc. An instruction that existed because beginning modelers sometimes forgot it and learned the importance of the grip change in a rapid and educational way. The early flips were exploratory. The engine was cold. The fuel had not fully reached the combustion chamber. The needle valve setting was approximate. You were gathering information. Each flip that produced nothing told you something. The engine is not flooded. The plug is warm. The compression feels right, or it does not. You learn to read compression by feel, the resistance of the piston at the top of its stroke communicating through the propeller blade to your finger, a specific pressure that said either yes or not yet. When the engine coughed, that first cough, that one-syllable bark that told you something was about to happen, you had to resist the urge to do anything dramatic. The tendency of beginners was to flood the engine at this point, to reach for the primer out of excitement, to try to force an outcome that required patience rather than intervention. The engine that coughed needed a small needle adjustment and another flip. That was all. The experienced modeler knew this, the way a craftsperson knows when to leave something alone. The novice learned it through the specific education of watching a flooded engine refuse to start for the next 4 minutes, while the fuel that should have been in the combustion chamber dispersed. When it ran, when the engine crossed from the cough and die into sustained operation, the needle valve became the art form. Rich was rough with a fat sound and incomplete combustion visible in the exhaust as a blue-white smoke. Lean was hard and high, a sound that carried warning in it. The sound of insufficient lubrication and excess heat that would, if sustained, make the experience of owning that particular engine considerably shorter. The right setting was in between, and finding it was a process of small adjustments. A quarter turn of the needle, listen. A quarter turn back, listen again. That took practice to develop, and that once developed, remained in the hands as a kind of mechanical intuition that transferred to other machines, other adjustments, other situations where patience and attention were the required tools. None of this was convenient. None of it was frictionless. None of it was the experience of opening a box and having something immediately work. And that is precisely the point. The friction was the education. The world that the OK Cub inhabited was also a world of workshop smells and late evenings in the particular domestic geography of the hobby in its mid-century form. Model aviation was not an outdoor activity only. Began indoors, at the workbench or the kitchen table, in the basement or the garage, with a flat box of balsa wood and a set of printed plans, and a bottle of dope that filled the room with fumes that no modern safety standard would tolerate and that people of a certain age associate entirely with creation rather than danger. The balsa came first. The ribs, the spars, the formers, cut from sheets by a die or a razor blade, sanded to fit, pinned to a building board over a plan that showed every piece in its correct relationship to every other piece. The structure of a model aircraft wing is a lesson in engineering. Why the rib has this particular profile. Why the spar carries the load in this particular direction. Why the covering has to be applied under tension and sealed with dope so it tightens as it dries. The fundamentals of structural engineering delivered in a form that a 12-year-old can engage with at a kitchen table. The OK Cub went into the nose of that model, the front of the fuselage, mounted on a firewall of plywood that the builder had fitted and glued during construction. The mounting was direct. 4 screws through the engine's case lugs into blind nuts embedded in the plywood, aligned so the thrust line was correct, which meant the model would track straight on the climb rather than rolling or pulling. The fuel tank was tin, usually small, maybe an ounce or two of capacity, because the Cub at full throttle consumed fuel at a rate that made a large tank unnecessary for control line flight. You primed, you started, you flew, you ran out of fuel, and the engine stopped, and the model glided to the ground in a circle or a straight line depending on how well you had trimmed it. Control line flight meant a pair of steel wires connecting the model to a handle in your hand, you standing at the center of a circle while the model flew around you. The wires transmitting your control inputs to the elevator through a mechanical bell crank in the fuselage. This was the entry-level relationship between pilot and aircraft that most of the hobby's participants of the 1950s and early 1960s began with. You learn to keep the model level, a harder thing than it sounds, because the natural tendency is to freeze on the handle when something goes wrong, which makes the thing that is going wrong worse. You learn to read the model's attitude by watching it, to respond to a nose-low condition before it became a nose-down condition, to understand through the handle what the wires were telling you about what the aircraft was doing. This was in miniature and in safety, the kind of learning that pilots undergo in actual aircraft. The feedback loop was shorter, and the consequences of error were lower. A crashed control line model was a disappointment and a repair project, not a tragedy, but the cognitive training was genuine. Reading an aircraft's attitude in real time, making control inputs before the situation became critical, developing the reflexes that allow a pilot to respond rather than react. These are learnable things, and control line model aviation was one of the places where they would learn it. And the OK Cub was the engine that made this learning accessible, at a price that ordinary families could manage, in a size that a child could handle, with a starting procedure that could be mastered through the specific education of failing at it repeatedly until you understood what it required. The Cub line expanded through the 1950s. The NAA, a remarkable of 1960, that was the last all-new engine design the Herkimer company would produce. There were diesel variants, the diesel and the diesel, both introduced in a period when the American market had largely moved to glow ignition, a somewhat contrarian position that reflected Charles Brebeck's genuine engineering interest in compression ignition rather than simple market following. There was a CO2 engine produced under an agreement with William Brown. There were marine versions with flywheels and pull cord starters, adapted for the boat racing community that ran parallel to the aircraft community in organization and culture. From 1955 through 1963, the Herkimer Company was reported as the world's largest manufacturer of model airplane engines. The full line covered the needs of almost every modeler in almost every application: free flight, control line. The early experimental radio-controlled installations where weight and reliability were critical, and the OK simplicity was an asset. The 700 distributors that the company had established gave it a reach into small-town America that the larger, more sophisticated engine makers sometimes could not match. An OK Cub could be found in the glass case of a hardware store in rural Pennsylvania or a five and dime in small-town Ohio. It was everywhere. In the way that tools and good, reliable, modest American products were everywhere in mid-century America, present without being extraordinary, trusted in the way that familiar things earn trust. Charles Brebeck died in April of 1963. His AMA Hall of Fame sponsor, William Moorbacher, wrote afterward that without Brebeck's designs and marketing philosophy, thousands of modelers who entered the hobby through the accessible price point and reliable performance of the OK Cub would never have joined at all. The specific contribution that the Herkimer company made to model aviation was not the fastest engine, not the most sophisticated, but the most democratic. The one that said model aviation was not for specialists only, that its pleasures were available to anyone who could afford a few dollars at the hobby shop counter and was willing to learn what the engine needed in order to run. What came after 1963 was a long, slow repositioning that the model aviation world underwent almost without noticing it was happening. The engines that emerged through the 1960s and 1970s from the Japanese manufacturers, OS engines, Enya, were, by any technical standard, better than the OK Cub had been. Better machined, better toleranced, smoother running, more consistent in their behavior. They started more easily. The needle valve was more responsive. The cooling was more efficient. They lasted longer under hard use. They were also more expensive initially, a real OS. Cost substantially more than an OK Cub, had cost, but as Japanese manufacturing efficiency improved and import economics shifted, the price differential narrowed. By the late 1970s, the Japanese engine was not merely the premium option. It was the common option. The American manufacturers who had dominated the engine market in the 1950s faced this transition from several directions simultaneously. The engineering quality bar had been raised. The price competition was intensifying. The market itself was shifting. The control line flying that had been the dominant form of model aviation in the Cub's heyday was giving way to radio-controlled flight, which required different engines, larger, more powerful, with throttle response characteristics that the Cub's design had not been optimized for. The Herkimer company had never built a radio control engine in the OK Cub size range, and the window for doing so had closed. The Comet debacle, a ready-to-fly model line that Herkimer had supplied engines for, whose commercial failure had nearly bankrupted the company, had left its mark. Ted Brebeck, Charles's grandson, had gone to the Comet factory and physically retrieved thousands of OK engines from the ready-to-fly models, preserving the asset while the business relationship dissolved. The company was restructured. The engine line continued through the legal entity known as Mohawk Engineering, before re-emerging as OK Engine Company headquartered in Mohawk, New York. The industrial heritage was continuous, but something had changed in the relationship between the company and the market it had once led. The hobby itself was changing in more fundamental ways. The ARF, almost ready-to-fly model aircraft began appearing in the late 1980s and accelerating through the 1990s. Aircraft that arrived from factories in China, already covered, already assembled, requiring only the installation of radio and power systems and a few hours of light work before they were ready for the field. The ARF was, from one perspective, the completion of the democratization that the OK Cub had begun, removing the barriers to participation in model aviation even further, extending the hobby's reach to people who wanted to fly without learning to build. From another perspective, the ARF was the end of what the OK Cub had represented, a technology that required you to understand something in order to use it, that gave back in proportion to what you put in. The hobby shop, which had been the social and commercial infrastructure of this culture for decades, was under pressure from multiple directions simultaneously. The large mail-order retailers, Tower Hobbies with its thick catalog arriving in mailboxes across the country, had been competing with the independent shop since the 1970s. The internet, when it arrived, accelerated this competition toward a conclusion. The shop that had stocked OK Cubs on its wall in 1965, that had advised 100 fathers on what engine to buy for their son's first model, was by 2000 either closed or surviving on a customer base that was aging in ways that no natural renewal was replacing. The children who had been 12 years old in 1952, kneeling over an OK Cub in a driveway, were 62 in 2002. Their children had grown up in a different world, a world that had year by year been offering more compelling alternatives to the specific pleasure of kneeling in a driveway with an engine that required negotiation. Video games, cable TV, the expanding range of organized youth sports that scheduled Saturday mornings for structured activity rather than the unstructured, barely supervised, frankly, slightly dangerous outdoor tinkering that the model aviation culture had always depended on. The field that a flying club had used for decades was increasingly hard to access, increasingly regulated, increasingly surrounded by development that made the noise of a two-stroke engine a problem to be solved rather than a sound to be expected. There is a question worth sitting with before this story ends, a question that goes beyond model engines and hobby shops and the specific cultural moment that the OK Cub inhabited. The question is about what happens to a civilization when the friction of mechanical engagement disappears from ordinary life. The friction was never pleasant, not in the moment. Flooded engines are not pleasant. Cold engine starts on a November morning with numb fingers are not pleasant. The stripped needle valve fitting that strips at exactly the moment when you most need it, not to, is emphatically not pleasant. None of these things were designed to be pleasant. They were the conditions of using a mechanical device that did not apologize for its complexity, that required knowledge to operate, that gave back its full capability only to the person who had invested the time to understand what it needed. What that investment produced in the people who made it is harder to measure and easier to observe. The person who learned to start an OK Cub, who learned to read compression by the feel of a propeller blade against their finger, who learned the difference between a rich sound and a lean sound and a right sound, who learned to adjust the needle valve in increments smaller than any measuring tool they possessed, by feel and by sound alone, that person had developed something. Not just a skill, though the skill was real and transferable, a disposition, an understanding that mechanical things have requirements, and that meeting those requirements is a form of respect, and that the respect pays off in reliable performance. This understanding transferred. The person who could start and tune an OK Cub could learn to service an automobile engine, could approach a plumbing problem with the specific patience that hydraulic systems require. The model engine was a school for the physical world, not because someone designed it to be that. Charles Brebeck designed it to make engines that worked, but because that is what engaging with a complex mechanical system at a young age actually does to the developing mind. What replaced this engagement? The question is not rhetorical. The skills developed through digital engagement are real and valuable and increasingly central to the modern world. But they are different skills, engaged through different senses, leaving different residues in the person who develops them. The screen does not have the smell of model fuel. The digital interface does not have the consequence of getting the mixture wrong. which is the specific, immediate mechanical feedback that teaches the relationship between adjustment and outcome. The loss of mechanical friction from childhood is not a disaster. It is a shift. It is worth asking whether the shift is fully understood, whether the specific capabilities that develop through the physical engagement with engines and tools and materials are being replaced by equivalent capabilities elsewhere, or whether they are simply absent. The OK Cub and the world it inhabited offer a concrete example of what the mechanical engagement looked like, what it required of the person who undertook it, and what it returned. The engine was never complicated by intention. It was made to be understandable, affordable, accessible. Charles Brebeck's design philosophy was democratic. The OK Cub was made so that anyone willing to pay attention could learn to use it. If you have stayed this long with this story, if any part of it has stirred something worth holding on to, share it with someone who built something as a kid or someone who wishes they had. Leave a comment below with your own memory of an engine that refused to start, or finally ran clean, or filled a field with a sound that carried farther than it had any right to carry. That is how this culture stays alive. Not in institutions or archives, but in the people who remember it and talk about it and pass some fraction of its knowledge forward to whoever is willing to listen. The OK Engine Company in Mohawk, New York, the successor to the Herkimer Tool and Model Works, was celebrating 75 years of manufacturing in the early 2010s. 75 years. From a machinist in a small New York City deciding in 1938 that he could build a better model engine than the one his son had brought in for repair. Through 1 million engines, through 700 distributors, through the Comet debacle, and the restructuring and the long repositioning that followed, the enterprise had survived. Not in the form it had taken at its peak, when the Herkimer Company was the world's largest manufacturer of model airplane engines, but surviving. Offering repair services for some of the 2 million model products the two companies had produced since 1938. Selling parts by U.S. mail, accepting credit cards, maintaining an email address where orders could be placed. Some fraction of the community that had grown up around these engines was still there, still maintaining them, still occasionally running them. The runner of an OK Super 60 in the early 2010s noted that the engine's needle valve was unlike anything they had previously encountered. Not a tapering cylinder in the conventional sense, but a tapering rectangular flat-sided bar, a shape that defied the intuition of conventional needle valve design. But that worked, clearly, because the engine ran in some fashion that the bar's particular relationship to the spray bar tubing made possible. This observation captures something essential about the OK engine line. It was built by machinists who were solving problems with the tools and the knowledge they had, not following the consensus of the industry. Brebeck's patents were real engineering contributions. The cooling jig for crankshaft fabrication, the geometry improvements that minimized heat distortion. These were solutions to real problems worked through on actual machines in an actual machine shop. The specific knowledge that went into those decisions is largely gone now. Not because it was lost, exactly, but because the world that required it stopped requiring it. The machinists who built those engines are gone. The shops that sold them are almost all gone. The fields where they ran, the control line circles worn into suburban grass, the free flight fields in the open country outside mid-sized cities, where a good thermal could keep a model aloft for hours, are mostly gone, or repurposed, or surrounded by development that makes them inaccessible. The engines themselves are not entirely gone. They are in garages and workshops, and the glass cases of collectors who understand what they represent. They are on workbenches, where someone with the patience to find the right glow plug and the right fuel mix is coaxing one back to operation. They are in the memories of people who are now in their 60s and 70s and 80s, who remember kneeling in a field with oil-dark fingers and the specific, urgent patience of someone trying to start something that requires understanding in order to work. Go back to that field. Go back to that driveway or that basement workbench where the light was dim and the fumes were real and the engine was cold and the whole afternoon was ahead of you. The OK Cub is in your hands. A machine so small you can hold it between thumb and forefinger, and yet so precisely engineered that it will run for hours if you understand it. You prime it. You check the compression. You flip the propeller and it coughs once, that single hard syllable, and then it catches. And the sound it makes is everything. It is not a complicated sound, but it is a sound that meant you had done something right, that you had paid attention, that you had learned what the machine needed, and given it what it needed and been rewarded with operation. That particular reward, the reward of a machine working because you understood it, is not something that can be replicated by any interface that stands between the human hand and the physical world. It is specific to the encounter with real machinery. It is specific to the moment when the engine catches. Some things, once they stop being taught, take a very long time to find their way back. The question of whether we find our way back to this one, to the specific, embodied, patient engagement with physical machinery that the OK Cub represented, is still open. The engine is still running in the hands of the people who remember. Whether it runs in the hands of the people who come after them depends on whether the sound carries far enough. The sound, at least, is still worth making.